All right, chemistry class, welcome back. Great to have you here again, and we are going to dive into chapter 4. Just a quick reminder or review on what we've been talking about so far. Remember, we have been emphasizing a discussion on matter. Everything that you basically see around you is matter, anything that takes up space and has mass. That matter is really, really special, really unique. All the matter that you see around you has special properties, and because of those special properties, we can use them in certain ways. Okay? They have those properties because of their chemical composition, because of the way the electrons are arranged and how many protons they have. They have certain physical properties and certain chemical properties. And really, it is mostly the electrons that give an atom, an element, its special chemical type of properties, how it reacts. Okay, and so we're going to be focusing on those electrons. Remember the model that we looked at for an atom told us that the nucleus is a dense core, and inside that nucleus you've got your protons, your neutrons. But then outside that, you basically have this large region of, it's mostly empty space. And in there is where you've got your electrons. We're not going to talk specifically right now about where they are located. You can just think about them in this kind of cloud area around the nucleus. These electrons are amazing little things. Remember, they don't have any mass, they have a negative charge, but still they are predominantly responsible for how an element reacts. So we're going to focus on electrons, and specifically we're going to focus on how those electrons are arranged in an atom. Very, very important. Take a second, and if you would, in your notebook, your note sheet that you're going to turn into me, answer these two questions. First one's talking about the atom, what's in the atom, and the other one's talking about that gold foil experiment. Remember that? Rutherford shooting those particles through a gold foil and try to see what happened. So answer that right now, and then come back and we'll get into the notes for each section. Okay, let's dive into section 4.1 here. And if you remember, we had a very simple model of an atom. It has a nucleus where you've got your positive protons and your neutral neutrons. And then we basically said, all right, somewhere around here, we've got these electrons. And they could just be anywhere in this region, okay? Kind of like a bowl of soup with something in the middle and electrons just floating around. Well, now we've discovered that's not exactly the case. And so we are going to develop a new model for what an atom looks like, and specifically where the electrons are located. Okay? We are going to have to talk a little bit about light in order to do that, because it was an experiment dealing with light that helped scientists understand a little bit about the arrangement of electrons. So this is not a digression. This is still on the topic, but we are going to talk a little bit about light and its properties. Light is a type of electromagnetic radiation. Okay? So here's some things you need to know, and you can put this in your notes. This is for section 4.1, and you need to understand some properties of light. First thing you understand is wavelength. So put down wavelength, and this is the symbol that we use for wavelength. That is a Greek symbol called lambda. And the wavelength is basically the distance between corresponding points on two consecutive waves of electromagnetic radiation, or light, or any type of wave. It could be a rope that you're, shaking up and down. So here's an example, waves on a beach, for example. You have the top of the wave here, and the next top of the wave, that distance is going to be your wavelength. That is your wavelength. Okay? The other thing you need to understand is frequency. Well, frequency has to do with how many in a certain amount of time. And this is the symbol for frequency. It looks like a fancy V. It is the number of waves that pass a point in a given amount of time, usually a second. And the number of waves per second, another name for that unit is called a hertz. Okay, so a hertz Hz, Hz is the number of waves per second. You're going to want to write that down. So if we are standing at the beach and we see in 1 second's time, if we see all 4 of these waves pass, we would have 4 waves pass us per second, and that would be 4 hertz. Okay? Waves can have different wavelengths, shorter, longer. They can have larger or smaller frequencies, depending on what type of wave it is. Now, electromagnetic radiation, there is a broad range of electromagnetic radiation. The only part of it that we see is we call that visible light. But there's lots of electromagnetic radiation that we don't see with our eye. We can detect it with instruments, okay? So on one end, you've got gamma rays. Those are high energy, and they are high frequency, okay? They're very dangerous if you were to be exposed to gamma rays. X-rays. If you ever go to a doctor and you get your bone examined with X-rays because you might have a fracture or something, you notice that when you go in there, they might cover the rest of your body with a lead vest so that only a part of your body is exposed to the X-rays. Ultraviolet. Ultraviolet would be, that's the electromagnetic radiation that can burn your skin when you're at the beach out in the sun. Okay? Then we get into the colors that we see that our eye can actually detect. And at the high frequency, high energy end, you've got violet, and then it goes blue, green, yellow, orange, and red. Okay? Now you might have heard of Roy G. Biv. I'm spelling it backwards. R-O-Y-G-B-I-V. Roy G. Biv stands for red, orange, yellow, green, blue, indigo. It's not mentioned here, but it's one of them, and then violet. Okay? So this is the portion of the electromagnetic radiation spectrum that involves the visible light that we're familiar with. Okay? Then, on the other end, you've got infrared, you've got microwave, that's the, heats up your food, you got radio waves, and then longer waves after that. So I just want you to know that a very small section of the electromagnetic radiation that we're aware of is actually visible to us. All right, you should define electromagnetic radiation. It is energy that travels through space in the form of a wave. Make sure that is in your notes. And in the electromagnetic spectrum is all forms of that electromagnetic radiation that I just talked about right up here. Okay? Now, we are specifically going to talk mostly about light, and I mentioned already 2 properties of any wave. It has a wavelength, lambda, and has a frequency. And there's a relationship between these two and how fast the wave is traveling. So this is C is speed, and this is your wavelength, and this is your frequency. So let's just take these 2 measurements right here and see what happens. Let's say that we measure the wavelength to be 3 meters. And we count how many waves are passing us every second, and we end up getting, we calculate to be, let's say, 12 waves every second. That's a lot, okay? Every second, that's 12 waves. That's pretty fast. So if I wanted to find out how fast each wave, each crest is moving, then I know that there are 12 waves every second, and the distance between each wave is 3 meters. So if I multiply these together, I know 3 times 12 is going to give me 36 meters. This is just number of waves. It's not really part of the unit there. It's just a number. Meters per second. Meters per second. That is a velocity, a speed. C here is going to be speed. And for electromagnetic radiation, all electromagnetic radiation travels at the same speed. We call it the speed of light, and that is if it's in a vacuum, right? And that is a set number, okay? So this relationship right here is very important. Wavelength times frequency is always going to equal to the speed of that wave. All right? Now let's get into the actual experiment that was done, and from this experiment, what scientists discovered. It is called the photoelectric effect. You have to understand what this is. The photoelectric effect, write this down, it basically is the phenomena that metal gives off electrons when light shines on it. Light is carrying energy, remember? Light is carrying energy, and when that energy hits metal, the electrons get excited and something's going to happen. Okay, so they set up an experiment, made it look something like this. Basically, we're shining light in. This is light coming in. Okay, and when they did that, this is a piece of metal right here. This is the metal. They would shine light on this piece of metal, and what happened is this metal, they had this other piece of this rod here that was hooked up to a battery. The piece of metal and this rod were hooked up to a battery, and they realized that there was a flow of electrons from the metal to this rod to complete the circuit. So somehow electrons are being emitted. Electrons are being emitted when light hits it. That's interesting, okay? So that's the first thing. The next thing is that that amount of energy that was being emitted was not continuous. It was in packets. It was in packets. In other words, they had to shine enough light on there, enough energy for the electrons to be emitted. None of them would be emitted until enough energy was there. And those little packets of energy are called quantum. So quantum is basically a quantum of energy that can be lost or gained by an atom. Okay? And that energy is directly related to frequency, the frequency of the light that you are hitting the metal with. So this is E, energy, and here is frequency. And this H right here is just a constant so that you can equate the two sides. So E, energy, is proportional to the frequency of the light hitting the metal. That H is called Planck's constant, and it's always going to be given to you. It's just a number, and when you put that in there, it's no longer just a proportion, it is an equation, and you can equate the two. Here's really what you need to know. When frequency goes up, energy goes up. Remember the spectrum up here? These right here have very high frequency, 10 to the 19th. Down here, this was just, it gets smaller, 10 to the 9th. This is now no longer hertz, it's 100 megahertz. So now this is in 100 kilohertz. So this is very large. This is high energy here, high energy, high frequency. And low energy here, because there's a low frequency. Short wavelength, this is short wavelength. Short wavelength has high frequency. If the wavelength is short, you're going to see a lot of waves passing by you in a short amount of time. Here, this is long wavelength, and they have a low energy and a low frequency. Okay. So, basically, the idea here is that when this metal was being hit by light, this packet of energy, okay, these particles, a photon is a particle of electromagnetic radiation that has no mass and carries a quantum of energy. It just carries a packet of energy. So this is light here. This is just another word for a light particle. Okay? When those photons and those light particles hit the metal, then electrons were being emitted. And that helps scientists understand a little bit about how the electrons exist. Now, here's what they discovered. Electrons exist only in very specific energy states or energy levels. So I'm going to go back up to my experiment here. So they would shine light on this, and if the light didn't have enough energy, no electrons would be emitted. Nothing. So they try higher energy light, and they'd hit that, and still maybe nothing was emitted. And then they'd try higher. Finally, some electrons would be emitted. Okay? And then maybe they try higher, and then some electrons would be emitted. But it wasn't like if they just threw a little bit of energy, maybe a few electrons would be emitted. No, they had to reach a certain level. Nothing happened until they reached a certain level of energy. So that helps scientists realize that, oh, these electrons only will react or get excited from those the electromagnetic radiation if there's enough energy. They must be residing at different energy levels or states, not just anywhere. Remember our plum pudding model said they can just be anywhere around the nucleus. No, they're not just anywhere around the nucleus. They are in specific high density regions where you're most likely to find an electron. So here's what happens. Another experiment that was done is that they would pass, it's kind of the same experiment, but they would pass current through a tube containing hydrogen gas. And light was emitted. That light, here's the tube right here, hydrogen gas is in that tube. That light then was split using a prism. And they realized that, hey, there are different wavelengths inside of that light that's being emitted. Not all light was being emitted. It wasn't white light. White light is all of the wavelengths that we can see. Only specific ones were emitted. So when they split the light apart, it was kind of pinkish in color, pink light coming through, and they split apart, they found specific different lights that have specific wavelengths. Well, those correspond to the idea that electrons are at specific energy levels, not anywhere, specific energy levels. Okay? And this can be done for any element. Every element has its own unique pattern for emitting certain wavelengths. Okay? And it is called the emission line spectrum. Okay? So every element has its own emission line spectrum. Now, why does this happen? I'll tell you. So let's imagine, here's your nucleus, okay? Your protons are in there. And you've got these electrons that are somewhere around the nucleus. But they're not just anywhere. They are at specific energy levels. And only at those specific energy levels. So when light comes in and hits this atom, the electrons get excited. They absorb that energy. And if they absorb enough energy, they will go from one energy level up to another one. So imagine this electron right here gets hit with enough energy from light, it goes up to the next energy level. Well, when you stop shining light on it, then that electron is no longer going to have that energy, and it's going to lose that energy. And so it drops back down to the previous energy level, and when it does that, it has to release that energy, and it does it in the form of light. So it gives off light. You hit it with electricity, or you hit it with light, or you hit it with heat, some form of energy, and that electron gets excited, it goes up to the next energy level, or maybe the third, fourth, fifth energy level, but when it drops back down, when it drops back down, it is going to lose that energy, and it releases it in the form of light. Okay? So, the idea here is, when electrons are in their ground state, the ground state is the lowest energy level. When they get excited, they go up to an excited state. When they drop back down, they release energy in the form of light. Key point. Okay? Key point. By the way, this happens, you notice this all the time. When you burn something, you light a match, the chemicals in that match head are going to be excited and drop back down, and that color, the color of that flame is a result of those electrons going up to high energy level and then releasing that energy as they drop back down in the form of light. Fireworks. Different chemicals are put in fireworks. Why? Because those chemicals, when they get heated up and excited, those electrons go to higher energy level, but don't stay there. And then when they drop back down, they emit very quickly the different spectacular colors that you see in fireworks. Okay? All right. Now, basically, what we're going to do is we're going to talk about these areas where the electrons reside. They're going to be called, they're not exactly orbits, they're not like electrons, orbiting around the nucleus. It's not exactly how they are, but this model, this ancient model here, given to us by Niels Bohr, still kind of retain the word of an orbit. So these are going to be called orbitals, the regions where electrons reside. Okay? So electron orbits or orbitals or atomic energy levels can be compared to rungs of a ladder. When you stand on the first rung, you have the less amount of potential energy. You have little potential energy. Okay? You're not very high off the ground. All right? If you go up the ladder, you're going to have more and more potential energy, and when you fall back down, it's going to hurt a lot more if you're higher up, okay? Because you're going to be releasing a lot more energy. That potential energy is going to be turned into kinetic energy. It's the same thing with electrons. Electrons at the low energy level here, energy level 1, E1, they have less energy. If they get up here to E2, energy level 2, they have more energy. Energy level 3 has even more energy. So if you hit this atom with energy, heat, light, electricity, you might be able to, if it's enough, it has to be enough, because it's not just going to go halfway. It has to go all the way to the next energy level or not at all. And if you hit it with enough energy, it might go up here to energy level 2 or up to energy level 3. And then when that energy is taken away, and you're no longer hitting it with enough energy, then that electron is going to drop back down. And when it goes from high energy to low energy, that's when it emits light. High energy to low energy. It's going to emit a different wavelength of light if it goes from energy level 3 to energy level 1 as compared to energy level 3 down to 2. Okay? All right. So when an electron moves to a higher energy level, it absorbs photons, light energy, and then that's absorption. When the electron falls back down to a lower energy level, it's going to emit that photon of energy in the form of light. That is emission. Okay? All right, we're not going to worry about all of these series here. Don't worry about that. So that is 4.1. You have to understand that electrons don't just hang out anywhere around the nucleus. They reside at specific energy levels, and those energy levels are unique for every atom, every element. And in order to get an electron to move from a ground state, low energy level, to a high energy level, you have to hit it with enough energy. If you don't, it's just going to stay at the low energy level. Okay? High energy levels are only attained, excited states, when you hit an atom with energy of some form. And when they go up to a higher energy level, then they don't stay there forever. They drop right back down to a lower energy level and emit that energy in the form of light. Very, very cool, and it's really, really interesting how it was discovered, and then we benefit from that. Okay, we're able to use that in order to maybe capture that energy or do some spectacular things like create fireworks. All right, let's go into, you might want to take a little break here, pause, but we're going to go into 4.2 next. All right, let's talk about section 4.2. And in 4.2, I'm not going to require you to know everything in this section, and we're going to keep it fairly straightforward. So just stick with me, and I'll tell you exactly what you need to know. We're going to talk about a different model of the atom. Remember, we talked about the Bohr model. The Bohr model basically says there's a nucleus, and electrons are orbiting around that nucleus like planets around the sun. Okay? Not exactly the case. We're going to talk about a different model that talks a little bit more about, instead of orbiting orbitals like planets around the sun, we're going to talk about regions. Regions where scientists believe the electrons reside, where they hang out. And they don't always hang out in the same place exactly, but there are these regions where we believe they hang out. Okay? Because orbits and orbitals it's kind of hung on to that word, we're still going to call those regions orbitals. All right? You don't need to worry about all of this part here, this first section of this first part of the 4.2. Okay, you don't have to worry about that. But what we do want to know is we want to talk a little bit about the quantum theory. Quantum, a quantity. Remember we talked about quanta being an amount of energy. So quantum theory basically says that mathematically we've been able to calculate where the electrons might hang out because electrons have wave properties, and so complex calculations are done in order to figure out this. You don't need to worry about it. We still call them orbitals where these electrons hang out, but instead of paths, circular or elliptical paths around the nucleus, they are regions, three-dimensional regions around the nucleus where the electrons are going to be, okay? High probability that the electrons are going to be in these areas. So if you imagine that we have our atom here, and we're going to talk about, on an X, Y, Z coordinate axis system, we're going to talk about these regions and shapes where the electrons are going to be. We're going to come back to this in just a second, okay? We're going to come back to all of this. I'm first going to talk about the shapes of these different regions, okay? Well, here's our nucleus, okay? Remember, electrons are going to be at different energy levels. In the first energy level, that is closest to the nucleus, when electrons are closest to the nucleus, they are most likely going to be in a region that is spherical, somewhere around the nucleus in this spherical region. So this right here is kind of illustrating the area, region, orbital where an electron might be. It doesn't mean that it's going to be moving around the edge of that sphere. It just means somewhere in that sphere you're going to have electrons. Okay? That's at the first energy level. Since it is a spherical shape, we're going to call that an s orbital. Okay? Now, in the first s orbital, the first energy level, there's not a lot of space there. So you can only have 2 electrons closest to the nucleus at the first energy level. This is the first energy level. Okay? First energy level. Only thing that's going to be in the first energy level is 2 electrons maximum. That's the maximum number of electrons, and they're going to be somewhere in this spherical region. Okay? If you have more electrons, you go to another element and it has more electrons than just 2, then you're going to have to put those electrons are going to have to be in the next energy level. So a bigger sphere is going to be accommodating the next electron, the third electron, the fourth electron. So it's another sphere here, and that sphere is going to be larger than the first one, and this is at the second energy level. The second energy level, okay? And you're going to have, again, 2 electrons in that sphere. Now, because there's more space as you move further away, there's actually another shape, another region where electrons can reside. And we're going to call those p orbitals. So you've got s orbitals are spherical, and now we've got p orbitals, and this is what a p orbital looks like. It kind of looks like the infinity symbol, or sometimes called a dumbbell or something like that. And there are actually 3 different p orbitals. Each p orbital can hold 2 electrons, maybe 1 in each of the lobes there. Okay? But you can also have a p orbital in this direction and a p orbital in this direction. So you'll notice each of the p orbitals can hold 2 electrons for a maximum of 2, 4, 6 in all the p orbitals. The second energy level has p orbitals. So you're going to have a p orbital. This is the second energy level now. P orbital here. You're going to have a p orbital here, and you're going to have a p orbital here. Okay? And each of those can hold a maximum of 2 electrons if need be. Okay? That's the second energy level. The second energy level has an s orbital and 3 p orbitals. If you go to the third energy level, it also has an s. It's much bigger. It can hold 2 electrons. And it has p. they're bigger. They each can hold 2 electrons. I'm sorry. And then it's going to have also what are called d orbitals. And this is what a d orbital looks like, and that's not the only way it looks like. It also looks in different shapes and different arrangements, but just think about it like multiple, lobes, if you will. All right? I told you there's one s orbital in each energy level. When you get to the second energy level, you have 3 p orbitals. When you get to the d level, d orbitals, that's going to start to be in the third energy level. The third energy level, there are 5 d orbitals. Okay? And we're going to pause there. Won't talk about the f quite yet. All right? So you can have s orbitals, p orbitals, and d orbitals in your different energy levels. As you get further and further from the nucleus, higher and higher energy is going to be able to accommodate more and more orbitals. All right? So let me pause here. I'm actually going to show you a quick video that's going to show you the different orbitals in a visualization here. Okay? Okay, so this video is going to show us the different orbitals. Remember, these are just regions where electrons are most likely to live. Okay? This is where they're going to live. And this video is going to show us these different regions and help you visualize them. We have here, we've got our different axes. So you've got your y-axis, x-axis, and z-axis here. And they're going to they're going to float in each of the different orbitals and show you the different energy levels as they do. Okay? And I'll just kind of walk you through this. So the first one here is going to be our first energy level, and it only has a spherical shaped energy level, or orbital. So the first energy level has just one option for electrons, and it is spherical in shape. Okay, there it is. And you can have maximum of 2 electrons for each orbital. So the maximum number of electrons that can hang out in that region right there, closest to the nucleus, is 2, because electrons repel each other. They don't like to get really close to each other. They spread out. So first energy level, 1s is your only option in the first energy level. This is energy level 1. S stands for spherical. Okay? So once you put 2 electrons in here, that would be helium, by the way. If you go to the next element on the periodic table, it has 3 electrons. Well, they're not all going to be able to fit in there. So we're going to have to go to the next energy level. Here we go. The first region in the second energy level is also spherical. It's bigger, but it is now also spherical, and you can put 2 electrons in that larger sphere. That is the second energy level, and it is also spherical. So that's 2s. You can put a maximum of 2 electrons in there, just 2. But since you're now further from the nucleus, you have more area, and 2 electrons in that 2s can move pretty freely and also give room for others. So there should be room for some other areas where electrons reside in the second energy level. Here's what they look like. You've got, this is the p-shaped orbital, and it looks like a dumbbell, okay? And you'll notice that there's an x here because they are oriented certain ways. This one's oriented along the x-axis. So in the second energy level, 2, you have a p orbital. This one can hold 2 electrons, maybe at the 2 ends of this shape. So that is your 2p. Okay? And it hangs out somewhere like that. But there's also another p orbital along the y-axis in the second energy level. It can also hold 2 electrons. So 2 electrons could go in that orbital, maybe at the 2 ends. And another 2 electrons could go in the vertical p orbital. That's called your 2pz. So in the second energy level, we've got not just the spherical region, but you also have 3 p orbitals. So in the second energy level, you could have 2 electrons in the s orbital, you could have 2 electrons in the px, 2 electrons in the py, and 2 electrons in the pz. So you could have a maximum of 8 electrons in the second energy level. 2 in the s and 2 in each of the 3 p's. Okay? Now, if you've got more electrons than that, you're going to have to go to the third energy level. You're kind of full right now. If you've got 12 electrons, you're pretty much full here, and you're going to have to be bumped up to the third energy level. Sorry, 10 electrons. You got 10 electrons here. Sorry, not 12. Because you'd have 2 in the first 1s, and then 2 in the 2s, and 2 in each of the 2 p's. That would be 10. Okay, so now we got, if these are all full, you got 10 electrons in there. So now if you've got another electron, the 11th electron is going to go to the third energy level, and you always start with the s, the spherical region. Always start with spherical. Okay, so a larger sphere can accommodate, again, 2. Every of these shapes can only hold 2 electrons. And then the 3p along the x-axis can hold 2. The 3p along the y-axis can hold 2. And then the 3p along the z-axis can also hold 2. But since you are further from the nucleus, you don't just have s and p's, you now also are going to have d's. Okay? And they're going to be coming in just a second. What comes just before the 3d's is a 4s, and you'll understand this later on when we talk about the periodic table. But if we have to go to the fourth energy level, it also has a spherical region, and 2 can go in there. Okay? But for just a second, we're going to come back to the D, the 3Ds. And these are really weird shapes. You don't need to know these. I just want you to know the shapes of the S and the P. Okay? D now, third energy level. We're going to come back to the third energy level here. And you can put 2 electrons in each of these Ds, and there are going to be 5 of them. All right? Kind of weird shapes. One shape there, 2 electrons in that shape, 2 electrons in this shape, there's your second D in the third energy level. There's your third D in the third energy level. Here's your fourth D in the third energy level. And here's your fifth D in the third energy level. 5 D orbitals. 5 D orbitals when you start at the third energy level. Okay? So these are the different E regions where electrons can reside, and they are called orbitals. Remember, 2 electrons, only 2 per region. Only 2 per region. All right, let me go back to our note sheet here, and we'll talk a little bit more about. Okay, so let's talk about these energy levels and the orbitals in them. I'm going to be giving you some different numbers, because we can kind of give numbers, ascribe numbers to an electron, kind of like an address. You have an address for your house, well, electrons have an address as well. Their address is composed of 4 numbers. 4 numbers. Here are the numbers. The first number is going to tell you the energy level. That number is called the principal quantum number. Okay? So, you might have, for example, the first energy level, the principal quantum number is 1. At the second energy level, it's 2, 3, 4, etc. Okay? So that principal quantum number, we're going to use the letter N, is just telling us what energy level we're at. Then the next number is called the angular momentum quantum number, and it is telling us the shape of the orbital. Remember, it's either spherical, or a dumbbell P, or it's kind of the funky D ones, and we're going to use the letter L, and we're going to use a number there as well, and those numbers are going to be S is 0, P is 1, D is 2, F, when we get up to the higher energy levels, is 3. Okay? Then we have one more number, and that is called the magnetic quantum number. Okay? And that magnetic quantum number has to do with if there are more than just one P. Remember, there are 3 P's and 5 D's, and I didn't tell you this, but there are 7 F's. Okay? So that number is going to tell us which of those we have. So for example, if you have a px, py, pz, we're going to use numbers instead to denote that as well. Okay, so for that we could say, since there are 3, we could use 0, -1, and +1. That's how we're going to do that. Okay, and for the d's, there's a d, I think they call it x, y, or yz or something like that, but you got 5 different d's. And for that, we're going to use 0, and a -1, a -2, a +1, and a +2. Sorry, I got one too many d's there. Okay? And then the last number is going to be, remember there's 2 electrons per orbital. Well, those electrons, in order to be in the same orbital, the way they kind of hang out together without kicking each other out, remember they repel, is they're going to have opposite spins. They're going to spin opposite directions. And so in order to do that, we're going to give them, the last number here is called your spin quantum number, and it's either going to be a +1/2 and a -1/2. I don't know why 1/2. Okay? I don't know. All right? So we have 4 numbers. And here's how we are going to identify those numbers. Again, remember the first number is the energy level. The second number has to do with the shape. The third number has to do with the fact that you've got multiple P's and multiple D's. And then the last number is the spin, either +1/2 or -1/2. Okay? And I'll help you through this and make a little more sense of it as we go on. All right, let's talk a little bit about, we're not going to use the quantum numbers very much. I'm just exposing you to it. We're going to focus on mostly just writing S, P, and D when we write these electron configurations. Okay? All right. But let's look at this for just a second here, ladies and gentlemen, and let's compare the different energy levels. In the first energy level, you only have the S orbital. That's it. Okay, you just have one orbital, one S. That's all you have. All right, and you have a maximum of 2 electrons in that one S. You can only have a maximum of 2 electrons in the first energy level. In the second energy level, you have S and you have 3 P's. Okay, so you've got 4 orbitals, 1 S and 3 different P's. Remember, the P's go along X, Y, and Z axes. So the S orbital can hold 2. Each of the P's can hold 2. That's a total of 6. So the second energy level can hold a maximum of 8. Okay? When you get to the third energy level, you've got S, P, and D. There's one S orbital, one S region. That can hold a maximum of 2 electrons. You've got 3 different P orbitals. That's a total of 6 electrons, 2 in each. You've got 5 different D orbitals. That's a total of 10, 2 in each of those. A total of 18 electrons can be in the third energy level. The fourth, you've got S, 1S, 3P, 5D, and 7F. I didn't show you the shapes of the F because I don't know what they are. And if there are 2 in each of these, that's a total of 16 different orbitals, 2 in each of those, a total of 32 electrons in the fourth energy level. The fifth and sixth and seventh are going to be similar to the fourth because they only have S, P, D, and F. They would have other orbitals if we had more electrons or more elements on the periodic table. Okay? All right. I know that's really confusing, but we're going to keep working with this, and we're going to simplify it a little bit and just use the S, P, and D arrangement kind of configuration to help you understand a little bit where they are. Okay? All right. Keep working hard. I'm here if you need me. And we're going to go to 4.3 here. You might want to take a little break, and we'll come back here and talk about 4.3. So don't go away. All right, let's wrap up chapter 4 here, ladies and gentlemen. We have been talking about electrons and how they are arranged in an atom. Remember, we've been talking about these orbitals, these regions where electrons reside, and they reside at different energy levels. They jump from one energy level to the next energy level to the next energy level. And inside of each of those energy levels, there are different regions where they reside. Remember, there's the S region, the sphere, the P region, it kind of looks like a dumbbell or infinity sign, and you get the D regions and the F regions. Okay? Well, we're going to try to make it really clear here as far as where the electrons are going to be residing, where they're going to be hanging out, and what regions they fill first. And it's all dependent upon energy. They're always going to fill the lowest energy positions first. Okay? So we're going to develop what is called an electron configuration. It's basically just how are the electrons configured, how are they arranged. All right? So electron configuration simply tells us the arrangement of electrons in an atom. Please write this down in your notes for section 4.3. Okay? And it all depends on energy. The electrons are going to fill the lowest energy levels first. And this diagram shows you exactly which ones are going to be filled when. And then I'll show you a little trick on how you can always figure it out. And believe it or not, this is related to the periodic table, which we'll talk about in a future chapter. Okay? So the first energy level is always going to be filled first. And in the first energy level, remember, we only have the S region, the spherical region, where there could be a maximum of 2 electrons. Then, if there are more electrons, you will fill the second energy level. That's right here. The second energy level has 2 different shapes in them. It has S region, and it has 3 different P's. Here they are, 1, 2, 3. Okay? Notice the S gets filled before the P. If you still have more electrons after that, then you start to fill the third energy level. The third energy level has S, P, 3 of them, 1, 2, 3, and D, 5 of them, 1, 2, 3, 4, 5. Okay? Then we start to fill the fourth energy level. Now, there's a little twist here, a little exception. Before the 3D, maybe scientists discovered this later and they just didn't want to change the numbers or something, I don't know. But basically, the 4s is going to get filled before the 3d. So actually the order goes like this: 1s to 2s, then you fill the 2p's, then you fill the 3s's, then you fill the 3p's, and you'll notice the 4s is a little bit lower in energy than the 3d. So that gets filled next, then the 3d, then the 4p, then you start to fill the fifth energy level. I know there's a 4D and a 4F, but those are a little bit higher in energy than the 5S. So then we get the 5S, then the 4D, then you go back to 4D, then you go to 5P, then you go to the 4F, I think we go to the 4F, then we go to 6S, 5D, 6P, yep, and then you're going to do the 7S, 5F, and the 6D, or something like that. I know it looks really confusing. All this diagram tells us is the lowest energy orbitals get filled first. And it gets a little bit messy here when we start adding the D and the F's. The order there is a little bit different. I'll show you a real easy way to always know how they get filled. And then I'll show you later on how we know they get filled according to the periodic table. But the off-ball principle says the lowest energy orbitals always get filled first. Please write this down in your notes. Off-ball, named after a scientist, basically saying the lowest energy levels get first. How are we going to know which ones the lowest energies are? Well, this diagram shows it right here, but that's kind of complicated, so I'll show you a really easy way to always figure it out. We're going to list the different energy levels and the orbitals like this. 1s. That's all that's in the first energy level. Then the second energy level has 2s and 3 2p's. I'm not going to write the p separately. You just know that when I write 2p, there are actually 3 different 2p orbitals. Then the third energy level has 3s, 3p, and 3d. Remember, there are 5 d orbitals in the third energy level. 4s, 4p, 4d, 4f. See how I'm just adding another lettered orbital in each of the energy levels here, another orbital there. So we have now 4f, now we go to 5s, 5p, 5d, 5f, and we would have another one like a 5g or something, but we won't need it because there are not enough electrons or not enough elements to go into that level. 6s, 6p, 6d, and we don't need a 6f because we don't have enough elements for that, 7s, and 7p. Okay? And again, we don't need these because we don't fill them up. Here's how you know the order. You draw it out like this, and then we're going to draw diagonally. 1s gets filled first, then the 2s, then the 2p, and then the 3s, then the 3p, and then the 4s, then the 3d, 4p, and the 5s, then the 4d, 5p, 6s, then the 4f, 5d, 6p, and then 7s, and then the 5f, 6d, and 7p. That's the order in which they get filled. This little mnemonic tells you, this little model tells you how to do that. Okay? It'll actually be easier when I show you how it all fits the periodic table, because then you'll just see it right there. Okay? All right, the Pauli exclusion principle basically says that you can only have 2 electrons in each of the, well, no, I'm sorry, that's it. The Pauli exclusion principle says no 2 electrons have the same address. Okay, they can't be in the same arrangement. Remember, there are a maximum of 2 electrons in each orbital, but one spins one direction, one spins the other direction. So we could give it a plus 1/2 and a minus 1/2 if we're doing the 4 quantum numbers. Okay, and then Hund's rule says basically that if an orbital is filled with 1 electron, if you have 1 electron in an orbital, you keep putting 1 electron in all the orbitals in that same energy level, and then you go back and start to double them up. Okay, so for example, if these are all p orbitals here, there are 3 different p orbitals. You would put 1 electron, the up arrow there is showing you an electron that's spinning one direction. And then if you've got 3, there's 1 in each of the p orbitals, and as soon as you get a 4th one, you start to go back and double up, showing a down arrow here, the electron spinning the other direction. So you don't put 2 into an orbital on the same energy level if there's others that you can start to put 1 in, and then you go back and double up once they are all filled in that energy level. Okay? So for example, here's how you would do it. Here's one way to represent the location of the electrons. I'm listing the orbitals here in their increasing order level. 1s, then 2s, then 2p. Notice there are 3 of them. Then you fill the 3s, and then there are 3p orbitals. Let's say we have sulfur. Sulfur has 16 electrons. Here's how they would get filled in the orbitals. You would go 1s, and then the second one in 1s. Now the first energy level is full. You go to the second energy level and the 2s orbital. 1 electron, second electron. That's full. The 2p's, there are 3 of them. So you go 1, 2, 3, 1 in each of the 2p's, and then start to double them up because they would spread out before they start to double up. Okay, as long as they're all at the same energy level, all the 2p's are at the same energy level. What do we have so far? 2, 4, 6, 8, 10. We have 10 electrons. We need 16. So here, 3s, there's 11, 12. All of these 3p's are at the same energy level. So there's 12, 13, 14, 15, and then go back and double up. This is showing you the arrangement of the electrons and what region they are residing in when you've got 16 electrons by following all of the principles mentioned above. Okay? Now, we have 3 different ways to model the electron configuration. We can use the orbital notation, the electron configuration notation, or the noble gas notation. And I'm going to show you each of these as we go through. Okay? So let's take something really simple. Let's take, for example, we have hydrogen. Hydrogen only has 1 electron. So what's it going to be in? It's going to be in the 1s orbital. And this is one way to model it. You put 1s under a line and an arrow going up or down, doesn't matter, just 1 electron in that orbital. Or we can write 1s, and then this superscript is telling me how many electrons in that orbital. So 1s1 means 1 electron in the 1s orbital. So for helium, 1s, has 2 electrons, Both are going to be in the first energy level in the 1s orbital, or you can write it as 1s2. Okay? So these arrows are representing electrons, or a superscript is representing the number of electrons. Either way is fine. So if I have, for example, sulfur, and remember from back up here, let's just look in this here. This is sulfur. If I was to take this right here and write it as electron configuration notation, then here's what it would be. It would be 1s2. That's this one right here. 2s2. 2p6. This is 3s2. And this is 3p, but there's only 4. Okay, there's 2 more openings there for later for more electrons that might come in another element. But this is 3p, 1, 2, 3, 4. 3p4. And that is the electron configuration for sulfur. Okay? So the orbital notation is this right here. This is the orbital notation. Now, the noble gas notation, I'll show you that really quickly. If you look on the periodic table, basically, let's see if I can give you an example here. Here we go. Here's a good example. Let's go through this. Let's go through a couple of these here and fill it in, and then I'll show you the noble gas configuration. Okay? Now, right before that, we already did hydrogen. Hydrogen is 1s1, and helium was 1s2. Lithium has 3 electrons, so the first 2 in the 1s orbital, the third one in the 2s orbital, nothing in the 2p because we only have 3. So there's 1s2, 2s1. Beryllium has 4 electrons, okay? 4 electrons, 1s2, 2s2. Boron has 5. Now we're starting to get into the 2p. 1, 2, 3, 4, and we're jumping up to the 2p. So it's 1s2, 2s2, 2p1. Carbon has 6 electrons. So we got 2 in the 1s, 2 in the 2p, 1s2, sorry, 2s, 2s2, and then 2 in the 2p's. 2. Nitrogen is going to have 3, 4, 5, 6, 7. See, I can count how many electrons by looking at the configuration. And I know how they're going to fill as well. They're going to start to fill the 1s, then they're going to fill the 2s, then they're going to start to fill individually this energy level here, the 2p's, 1 in each. 1s2, 2s2, 2p3. Oxygen has 2, 4, 6, 7, 8. This is how they fill. You'll notice that 2 in the 1s, 2 in the 2p, and then 1, 2, 3, and then you start to double up. So this is a 1s2, 2s2, 2p, 1, 2, 3, 4, 4. Fluorine, 1, 2, 3, 4. How many electrons does it have? Well, it's got 5, 6, 7, 8. So these are going to be 1, 2, 3, 4, 5, like that. Oops, sorry, that's 9, isn't it? All right. 2, 4, 5, 6, 7, 8, 9. Oh, that is 9. It should have 9. Yep, it should have 5, 6, 7, 8, 9. My apologies. So there's 9. Okay? Now when we get to neon, neon's going to have 10. Look at this. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. 1s2, 2s2, 2p6. And notice everything is full here. If we had one more electron, we'd have to go to the third energy level. Now, it gets really tedious to keep writing these long electron configurations, especially when you've got 30, 40, 50 electrons. So here's an abbreviated way to do it. You're going to like this. You can only use this with elements. So you can only use this shortened abbreviation version with using the helium or the neon or any other noble gas, those are in the last column on the periodic table, to then add on to. Here's what I mean. you'll notice that all of these right here, all of these, they all start with 1s2, 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 1s2. So I don't need to keep writing that. I know that anything past helium before neon is going to start with 1s2. So I can write it as helium, and I put it in brackets, and that takes care of the 1s2. And then I would write just the remaining part of that. So for this one, helium, and then, 2s1, and then 2s2, helium, and then 2s2, 2p1. And for the next element here after neon, it's going to have 11 electrons. So I could write, instead of writing all of this, I know this is going to be the beginning, I could just write neon and then 3s1 and done. That would be for the next element after neon in the third row, starting the third row. This is called, I mentioned it up here but didn't show you yet, this is called noble gas notation. Only the noble gases can be used in place of something. Helium is a noble gas. Neon is a noble gas. Only the noble gases can be used in this method. Okay? And then you just add on what is additional. All right. Here's what we're doing there. This is a good example right there. Here's sodium, but instead of writing the long electron configuration, we know it's going to have everything that neon has in it plus the 3s1. Magnesium is the second element in the third row. It's going to have everything in neon. Neon's the end of the second row plus 3s2. Aluminum, same thing. It's going to have everything that neon has, and in addition, 3s2, 3p1. You get the idea. Okay? Oh, here's that diagram, that model I showed you. So it shows you the energy order in which these orbitals get filled. Okay? And that basically is going to wrap up this section. You can see there's some more examples here. You can look, I would encourage you to look at all these and see if you can figure out how many electrons go in each of these orbitals here. And notice that we're writing the noble gas notation right there for you as well. Okay? You see how much we're saving here. Instead of writing a long electron configuration, we're putting the noble gas from the end of the previous row, and then just adding on what we have. Okay? Okay. Here's the fifth one. Notice we're starting to get the D's. And then the sixth. Okay. Now, when we get to the periodic table, I'm just going to give you a little bit of some foreshadowing here. When we get to the periodic table has these specific regions or blocks on them. We call them blocks. And that's basically where those different orbitals are getting filled. All right. So you'll notice right here, this block right here, column 1 and column 2, are 2 columns long. That's because that's where the s orbitals are getting filled. S orbital can have 2 electrons in them, right? This block over here this would be 13, 14, 15, 16, 17, and 18 columns. And there are 6 of those there, 6 columns. That's because that's where the p's are getting filled. Remember, there are 3 p's, 2 electrons in each. That's 6. There are 6 columns right there. D's, there are 10 of them. Well, guess what? Here are 10 columns right there. That's where the D's are getting filled. And then F, there are 7 of them, and 2 in each, so that's 14. Here's 14 right there for the F block. And we'll talk more about that when we get into the periodic table. Okay? All right. Take some time and look at these review questions. Ask questions if you got them, and I'll try to remember to send you answers and help you out whenever you need it. Don't hesitate to reach out to me. I know this is a lot of information being thrown at you. We'll keep reviewing it and give you lots of practice in order to master it. Okay? Keep up the great work.